Morning, good morning.
Good morning, sir.
Yes. Good morning, Giridhar. Good morning, Mita. Right. So I think we can start right away. Right. Everybody is here. How many people are there? I have 9 people. I think good enough strength. Right. So we'll start. Let me share the screen. Oh, like basically for 12 students, I conducted a quiz. So that's what happened. Right, last class, I guess, what we see, yeah, started with the chemical bonding chapter, right? So we saw what is a bond, why a bond, right? Where is it? Start. Oh. Yeah, right. So we started with okay, what is a bond? A bond is nothing but an attractive force that is between the molecule, between the atoms. And why a bond is formed? Because right, why a bond is formed is because the atoms involving in the bond formation are getting stability. That's why a bond is formed. Okay, then we went on to see that there are 2 types of bonds in chemistry. One is what is called as primary, the other one is what is called as secondary. Now, the basic difference between them is we have to go for the Dalton's theory. It says that atoms undergo some kind of modification or say some kind of rearrangement which during a chemical reaction. And if you understand where the rearrangement is happening, then we'll be able to answer the question. And we answer the question that it is going to happen in the electronic configuration of an atom. Right? So if there's a complete change in the electronic configuration, then it comes under primary. If it's only partial rearrangement, then it comes under secondary. And we saw what are the different types of primary and secondary bonds. Ionic bonds, covalent bonds, coordinate bonds, metallic bonds, all these comes under primary. And in secondary, I have all these things: dipole-dipole interactions, dipole-ion interactions, van der Waals forces, hydrogen bonding, all these comes. Then we went on to see what is an ionic bond. We already know there is a cation, anion. Obviously, there's a positive charge, negative charge, a huge, strong force of attraction, right? And what are the favorable conditions for the ionic bond to be formed? The element forming the cation should have less ionization energy, and the element forming the anion should have high negative value of electron gain enthalpy, right? And then this we missed periodic, diagonal relationship, and then went on to see what are the properties of ionic bonds. The first property is that the bond is very strong. And since the bond is very strong, they have high boiling points and melting points. And we even saw what do you mean by polar, right? For polarity, what you have to look into? You have to look into the difference in electronegativity between the bonding atoms, right? More is the difference in electronegativity, more will be the polarity. Now I already understand that I have a highly electropositive element forming the cation, high electronegative element forming the anion. So obviously there is huge difference in electronegativity, right? So thereby they are highly polar. And since they are highly polar, they are going to be soluble in water, right? Because water I know is a polar solvent. I think I asked you to remember phrase like dissolves like, right? If there is one type of substance that will get dissolved only in that type, there are only 2 types, polar and non-polar. Polar solutes dissolve in polar solvent, non-polar solutes dissolve in non-polar solvents, right? And then we said that their aqueous solutions or molten states are going to be good conductors of electricity. It's because they have ions. The charge carriers are there. For anything to be a conductor, I should have free charges. Free charges means charges which should be there, which should be able to move inside the conductor. Only then there'll be good conductors of electricity. Obviously, I understand that there are ions which are charges, so that's why they're responsible for the conduction, right? And then the last 2 points talk about the structure. All ionic compounds form highly ordered crystal structures, okay? And these crystal structures are what are called as lattice, okay? Right, and these crystal structures are very strong, very stable structures, right? Okay, so that I say that they have very high lattice enthalpy. Lattice enthalpy, the perfect way to define them is it is the energy released when the lattice is formed. Huge amount of energy is released. That means that the compound is highly stable. The lattice structure is highly stable. Okay, so this is where we stopped last class. Okay, now there were questions like, sir, like NAF, NaCl were there. Like, how do we say that this is more ionic or less ionic? We'll continue with that today. Okay, so we are going to see covalent nature in ionic compounds. Okay, there is going to be some covalent nature existing in ionic compounds. We'll understand why, and we'll understand how to compare two ionic compounds, which is more ionic, in the sense that whichever is having more amount of covalent nature, it is less ionic. Whichever is having less amount of covalent nature is highly ionic. That's what we're trying to see today. Not today, I mean, not the entire class, one topic. Okay, right. So for me to understand how even covalent nature exists, right, I have to understand this term called as polarization. Okay, this term I have to understand what do you mean by polarization. Okay, now what we understand is, people, there is a cation, right, and there is an anion. Generally, anions are bigger than the cation, generally speaking. We already know, we saw it from the periodic table, right? Cations are smaller than the parent atom, and the anions are bigger than the parent atom. Okay, right. So what is going to happen now? Those two will be there. There'll be electrostatic force of attraction. Everything will be there. But in addition to that, what is going to happen is, now there will be some electrons here on the negative charge, on the anion, right? Okay. Now what is going to happen is this: when I put a circle, right? When I put a circle, it is perfectly all right, right? But this will not be a perfect circle because of the presence of the positive charge. Okay, so what is going to happen is, this positive charge is fine, but if you look at the negative charge, that is the anion is going to be somewhat, I'll draw it properly once again. The anion is somewhat getting distorted. Okay, the anion is somewhat getting distorted in the sense that this electron is coming closer to this particular cation. Why? Obviously because the positive negative charge attraction, right? There's a positive charge, the electrons are there in the valence shell, and these electrons are like, the electron cloud is symmetrical here, but this will not be the reality. In reality, what happens is, this electron cloud is getting distorted. Okay, now this phenomena of distortion, right, the polarization, how do I define it? It is the distortion of the electron cloud. Okay, this is the distortion. Like, what is polarization? Polarization is nothing but distortion of the electron cloud. The electron cloud is properly oriented here, but in reality, what we see is that the electron cloud is not properly a circle. It is going to become little distorted because of the presence of the cation. The electrons are going to come closer to the cation. Okay, now you can ask me, sir, will polarization happen in cation also? Yes, it will happen, because I know this is a highly electronegative atom. The electrons on this can also get little distorted. Okay, but this distortion happening here is comparatively very less compared to the distortion happening here, right? So I would say, compared to this, right, this is negligible, right? Compared to the distortion, or compared to the polarization happening in the anion because of the cation, the polarization in cation due to the anion is very negligible, but it is happening. It's not like it's not happening, it is happening. Right. So what are you trying to understand here? This is a perfectly ionic bond, but because it is little getting distorted, is it not like the electron is coming and getting shared between the cation and anion? Right. So that is why we say, because of polarization always brings in some covalent character. Right. The process of, or the phenomenon of polarization, right, always brings in some covalent character. Right? What is polarization? Polarization is the distortion of electron cloud because of some other species. Okay.
Sir,
yeah, tell me.
Sir, the polarization in cation is negligible.
Yes, correct. It is negligible. Correct. Yes, was that a doubt? Okay. Good.
Yes, sir. Understood.
Understood. Right. Great. Great. Right. So polarization will happen in cation, but it is very, very small compared to the polarization happening in the anion. Okay. So now you understand that the electron, if it is perfectly here, no sharing, but if the electron is little trying to come closer, it is almost as if it is getting shared between the anion and the cation. Correct. That is why we say that it is bringing in some covalent character also due to polarization. Okay, now the point that how covalent nature exists in ionic compounds is very clear to us. Right now, what we have to understand is if I give you two ionic compounds, how do you compare where the covalent nature is high or say where the ionic nature is high? How do you compare that? Okay, so for that, we have to speak individually. It depends on the cation. It depends on what anion I have, depends on what cation I have. All these things matters. Okay, right. So now you understand that the cation is the one which is polarizing the anion. It is because of the cation, the electron cloud is getting distorted in the anion. Okay, so whenever we speak about cation, right, we use this term called as polarizing power. Right, we use this term polarizing power. That means the ability, how do I define polarizing power? It is the ability of the cation to polarize the anion. Very, very simple. This is not polarizing power in the sense, it is the ability of the cation to polarize the anion. Right? Now, what you have to understand is, people, more and more polarization happens, more and more is the covalent nature. Is it not? Because the more and more the electron will come closer and getting shared between this cation and anion. Isn't it? So more and more in general, more and more polarization, more and more is the covalent nature. Right? So obviously what I understand, if the polarizing power of the anion is very high, obviously more polarization will happen. Obviously more covalent character will be there for that particular compound. Covalent nature. Right? More polarizing power, more covalent nature. Right? Now, how do I decide which cations will have more, what kind of cations will have more polarizing power? Right. So for that, we need to understand this point that the polarizing power is directly proportional to the charge density. Right? The polarizing power is directly proportional to the charge density. Is it not? It's very easily understandable. Is it not? When I have a very strong positive charge, obviously more and more will be the attraction towards the electron, and more will be the electron coming towards this cation. Is it not? Right? So more and more is the charge density, more and more is the polarizing power of the cation. Now, instead of speaking charge, now we know what is charge density, right? Charge density is charge divided by the volume or size, whatever you want to call it. Right? So if I bring them into two different categories, charge and size, if I consider them as different parameters, you can easily tell that the polarizing power is directly proportional to the charge. Obviously not. More and more is the charge, more and more is the attractive force. Right? And it is inversely proportional to the size, because you can understand size comes in the denominator. Right? A smaller cation has more polarizing power than a cation which is very big. Same way, a cation having say +1 charge is having less polarizing power than a cation which is having +2 charge. Hope you're all getting this point. This should be in your fingertips. Okay, and whatever we are seeing here, we are comparing, right? Basically, these rules, whatever I wrote here, the polarizing power is directly proportional to charge density. That means it is directly proportional to charge and inversely proportional to size. All these are some rules called as Fajon's rule. Okay, F-A-J-A-N, Fajon's. Fajon is a scientist. Okay, Fajon's rule. Right. So now, if I take some examples for that matter, right? Say I take NaCl, MgCl2, and AlCl3. Okay, all the anions are same. Anions are chlorines, right? But look at the cation. Cation, here is sodium, here it is magnesium, here it is aluminium. Is it not? Now, how will you do it? I'm asking you to arrange them in the order of covalent nature. Okay, arrange them in the order of covalent nature. Now, since all the anions are same, all you have to look into the cations. What are the cations? Na plus is there, Mg2 plus is there, Al3 plus is there. These are all the cations. Now, what did I tell you? More is the polarizing power, more is the covalent nature. Right? Now, how do you decide the polarizing power? In this particular case, you have to look into the charge. The first priority always is the charge. Second priority only will go to the size. Okay, first priority goes to the charge, second priority only will go to the size. Now you look into this, this is +1, this is +2, this is +3. Can I say the polarizing power of Al3 plus is the greatest? It is greater than Mg2 plus, and Mg2 plus has more polarizing power than Na plus, right? So now if I ask you to arrange them in the order of covalent nature, this is how you will arrange. Right? If I ask you to arrange them in the order of ionic nature, then obviously you'll put the opposite. Wherever the covalent character is less, there the ionic character is more. Right? Is this point very clear to everybody? Is everybody okay? Can I get a yes from everyone?
Sir, is size basically Yes, same sir. in all the three cations?
No, obviously it will not be same, right? I know Mg2 plus will be a little smaller and stuff, but what you have to understand is the first priority will always go to charge. If the size, if the charge is same, then I go for size. That is how I do it.
Okay.
Right? Is everybody okay, people? Everybody understood how is it that the covalent nature order is like this? Everybody understood? Because it's just based on the polarizing power. More charge, more polarizing power, and more covalent character. Very, very simple. Right?
Sir?
I hope everybody is able to get this point. Right. Now, let me take a case where I have to take into account of size. Right? Say I take LiCl, NaCl, and KCl. Right? Now what happens? The anion is same. Again, chlorine, fluorine, fluorine. Right? But the cations are different. Here it is, I know it is Li plus. Here it is Na plus. Here it is K plus. Is it not? Now you see all of them are 1, 1, 1, plus 1, plus 1, plus 1. If you see these kind of situations, then you use the size. You tell that the polarizing power is going to be inversely proportional to the size. So the cation which is having the least size is going to have the maximum polarizing power, and that maximum polarizing power will give rise to the maximum covalent character. Right? Now think about this and tell me, which is the one which will having maximum covalent character in these three?
Li.
Li, right? Because Li is the smallest. Sorry?
Yes, sir. Potassium.
Potassium will have the highest polarizing power.
Yes, sir.
Now look at this, right? Now I told you polarizing power and size are inversely related. Smaller cation will have more polarizing power than a bigger cation.
Oh, okay, sir. So Li.
Exactly, right? So Li is the smallest, sodium is a little bigger, K plus is the biggest, right? So obviously if I ask to arrange them in the order of covalent nature, right? Since Li plus is the smallest, that will have the largest polarizing power, largest covalent character. So this is how it goes. Okay.
Sir?
Yeah, tell me.
Sir, in the previous example also, even with respect to the size,
It works.
it's still true, right?
Correct. It's still true because I know Mg2 plus will be smaller than Na plus, Al3 plus will be smaller than Mg2 plus. Absolutely, it works. Why not? Right? Good. That's a good observation. Right? Okay. So I hope everybody understood. How are we going to decide the polarizing powers? Based on the polarizing powers, how do you decide the covalent nature? Right? Yeah. Tell me.
Sir, can you explain logically why polarizing power is inversely proportional to the size?
It's not directly related to this, but what you have to understand is about the charge density. Right? A smaller cation with a high amount of charge will be very strongly attracting the electron. Are you able to get the point? Right?
Sir,
A smaller cation.
If it was bigger and it had more power, then it would easily attract more, right?
If it has big, if it is big, say for example, the charge is +1 in all these cases, right? The charge is +1 only in all these cases, correct? But a smaller cation having +1 than a bigger cation having +1, right? Obviously, it's like this. Or how do I put it?
Volume is different now, sir.
Yeah, obviously the volume is different. So volume is different means what will happen? So obviously a high charge density in a small space, huge amount of charge is there. So obviously that will have a very, very strong attractive force for the electron. That is how we explain it. Yes, do you get the point?
Sir, so the smaller one will have more non-metallic character.
You should not tell non-metallic here. Non-metal or metal can have ionic nature or covalent nature. You should tell since the smaller cation will have more covalent nature. That's why you must tell, not non-metallic. Yes?
Okay, sir. Yes, sir.
Because
Sir, I have a
chlorine,
doubt.
one second, chlorine here is again a non-metal only. Just because chlorine is there, you will tell that it is having more covalent nature? No, it is not based on that. Yes, what's the question, Sukriti?
Sir, the polarization also depends upon the anion, right?
Absolutely. Coming to the point, we complete only cations. We'll come to the anion now. Anion also makes sense, right? We'll come to that. Okay, now cation is very clear to everybody. Any questions anybody has? Okay, fine. I hope everything is clear. Right. Now moving on to anions. Right. So for anions are the one which are getting polarized. Okay. So the term which I will use there is what is called as polarizability. In the sense that how do I define this is nothing but it is the ability of the anion to get polarized. Very, very simple, right? So obviously more is the ability of the anion to get polarized, or say more is the polarizability, more and more is the polarization, right? And more will be the covalent nature, right? More and more will be the covalent nature. Okay, right. Now the next question comes to our mind is, sir, how do I decide the polarizability? Coming to the point. Okay, so for polarizability, right? The first criteria is again charge. Okay, now obviously what I understand is more amount of charge, right? More is the polarizability. Now it is very easily understood, is it not? Now if I have more amount of negative charge, more amount of electrons will be there. More amount of electrons will be there. Obviously, that particular electron can be easily distorted in the sense that it can easily come out and get shared between the cation and anion. Okay, so polarizability. I'm talking about the charge of anion, people. Okay, so I'll say for okay, we'll come to the point. So more polarizability means more charge means more polarizability. That's very easily understandable. More is the charge, more will be the attraction. I mean, I'll say more will be the electron, and more will be the attraction between the electron and the cation. That is how it will be. Right. Okay. The next one is my size. Now, size and polarizability are again directly proportional. Now, again, it's very easy to understand how is this, right? Say, I have an anion which is a little small. I have an anion which is very big. Now what happens? This electron will find it very easy to get distorted because this electron is not that tightly bound to the nucleus. Is it not? But here in this case, this electron is very tightly bound to the nucleus. So this getting polarized is a little difficult compared to the case which I have here because the electron is not that strongly held. Right? So that's why we say polarizability and size of the anion obviously is directly proportional. Obviously more size means more covalent character, right? So again, these two are the phejons for anions.
Sir,
Yeah.
Sir, earlier when you said that cation has less polarization, did you mean that suppose the electron of the anion has less space to get distorted?
Okay. I'll explain exactly what you want to hear. The thing is, cations are generally very small, right? Cations are generally very small. Now, this whatever the explanation I gave you here holds good for cations also. Generally, cations are very small, so the electron in the cation will be very strongly held from the nucleus. So those coming out and getting polarized is very difficult. Or in other words, I already have a positive charge. Right, I already have a positive charge. Removing an electron from positive charge is very difficult, very, very difficult. Because already it's a positive charge. Already I'll have very strong force of attraction between the positive charge and the electron. So removing the electron there is again a very, very difficult process. That's why we say that in cations, polarization is happening, but it is very, very small, very, very negligible. That's why we say that. Yes, understood?
Yes, sir.
Okay, good. Right. So now keeping these two points in mind for your anions, right? We'll look into some examples. Right. Say I have NaCl, Na2O, Na3N. Okay, NaCl, Na2O, and Na3N. I want you to arrange them in the order of covalent nature. Okay, now again, you see the cations are same, right? The cations are same. The only difference is happening in the anions, right? So what are the anions here? Cl minus, O2 minus, and N3 minus, right? Now, what did I tell you for polarizability? More and more is the charge of the anion, more and more is the polarizability, and more is the polarizability, more and more is the covalent character. Correct? Right? Now you see that this is -1, this is -2, this is -3, this is having the maximum charge, so maximum polarizability, maximum covalent nature. So this is how the polarizability will change. So obviously based on that, I can tell that this will be the order of covalent nature. Na3N is more covalent than Na2O than NaCl. Okay.
Sir,
Yeah, tell me.
here also the charge is the first priority.
Here also, yeah, exactly. Charge always is the first priority, then comes the size. Yes, correct. Okay,
Okay,
right.
sir.
Good. Okay, so now that's about difference in the charge. We'll take an example where there's difference in size. Say, let me take NaF, NaCl, NaBr, and NaI will not take. NaI, if you want, you can take, not a big deal. Right? So I have these things. Now, again, I ask you to arrange them in the order of covalent nature. Right? Again, what you see is that the cations are same. Right? Only the anions are varying. Let me see what are the anions here. F minus, Cl minus, Br minus, and I minus. Now, what did I tell you for polarizability? More and more is the size of the anion. Be easier and easier it is for the anion to get polarized, or say more and more is the polarizability. Right? Now, obviously, when I go down the group, all these belong to the same group. So down the group, the size increases. More size, more polarizability. I minus has the maximum size, so maximum polarizability, maximum covalent character. So this is the order of polarizability. Right? And obviously this would have been the order of covalent character. CC, I write means covalent character or covalent nature, CN, right? Okay, right? So like this, I obviously understand that even though it's ionic compound, there will always be some covalent character because of the polarizing nature of the anion and polarizability of the, polarizing power of the cation and polarizability of the anion. Okay, right? So this question I think was asked by, I think, Sridhar, what's the name? I forgot. This question was asked by whom yesterday? There's NaF and NaCl, something someone asked, right? Who
Sir,
was that?
I asked, sir. Raghav.
Raghav.
Okay. Raghav. Yes, Raghav asked this question. Yes, correct. Okay, now is it clear, Kana? Right, what was the question you asked? How are you going to do this and all that? Right?
Yes, sir. Now you told about covalent nature, so ionic nature, it will be the reverse.
Exactly. Covalent nature and ionic nature are inversely related. Whatever is the order you get for covalent nature, the reverse will be the order for ionic nature.
So NaF will be more ionic.
Ionic than NaCl,
Okay.
than NaBr, than absolutely. Okay, right, fine. So that's about covalent. Something went nice once again. Yeah. So that's about covalent nature and ionic compounds. Okay. Now in covalent compounds also I can have ionic nature. That we'll see when I see about covalent compounds. Okay. Once we complete covalent compounds, I'll tell you how is it that the ionic nature exists in covalent compounds. Okay. Right. So moving on, that's all about your ionic compounds. Ionic compounds are done, right? Ionic bonds and such are done. right? So now we'll move on to your covalent bonds. Okay, now this is going to take up most of the chapter, right? And ionic bonds are very less is there. There's nothing to study much. But say covalent bonds, I have a lot of things to study. Right. Okay. So we already know how a covalent bond means what. Here it happens by mutual sharing of electrons. I have been using this term from my lower classes. Is it not? It's by mutual sharing of electron. Anyways, now before we move on to see how the electron is shared or whatever, so on and so forth, we'll try to understand the physics behind covalent bond. How is it that the covalent bond is formed? Okay. Right, fine. Now, see, when I say an isolated atom, right, there was a lot of question. Ionization enthalpy is defined for isolated gaseous atoms, right? So when I say an isolated atom, only for an isolated atom, I will be able to speak about the electronic configuration. Because obviously, because some other atoms are there nearby, it will influence the electronic configuration, maybe in little way. Right. So remember that for isolated atoms only, I'll be able to speak about the electronic configuration. Right. An isolated atom is one which is free of the influence of all the other neighboring atoms. Those are what are called as isolated atoms. Okay. Now, when the atom is isolated, there is no problem. Right. But say if there are two atoms in the nearby vicinity, right? If there are two atoms in the nearby vicinity, what is going to happen is there is a nucleus here. And there is I'm talking, say for example, let me take the case of H2 molecule. Okay, say this is one hydrogen atom and this is another hydrogen atom. Okay, now each of these hydrogen atoms have have a nucleus. Okay, and each of these hydrogen atom has one electron. Okay, right. Now, what are we going to do is that say these two are isolated now, right? Initially, these two were isolated in the sense that there is no interaction between the neighboring atoms. Okay, now what I'm going to do is that I am going to bring them little closer. Okay, I am going to bring these two hydrogen atoms a little closer. Now what is going to happen is that the nucleus of this is going to attract the electron of this. Same goes here. The nucleus of this are going to attract the electrons of this. Okay, so the nucleus of one atom and the electron of other atom, obviously nucleus is positively charged, electron is negatively charged, so they are going to get attracted. Okay, say when they are isolated, when they are very far away from each other, there is no such interaction. The nucleus of this and the electron of this are intact, right? But I am just bringing them closer and closer and closer. At some point of time, this kickstarts. What kickstarts? The interaction between the nucleus of one hydrogen atom and the electron of the other hydrogen atom are going to get attracted. Okay, now I don't have to do anything. Because of this attractive force, the hydrogen atoms will come closer and closer and closer. Okay, right. Now, they will come closer and closer and closer. Say their potential energy will be keeping on decreasing because they're getting stabilized because of the attractive force. Right. Now, when they become so close to each other, right, initially very far away, I put them in a position where the attraction force starts. Now they keep on coming closer and closer and closer. There'll be a point of time that they'll be very close to each other. At that point, repulsion will come into the picture. Repulsion of what? Nucleus repulsion, electron repulsion, because they're very close by now. Right, so there is going to be some repulsive forces which will try to push the atoms away from each other. Is it not? So at some distance in between, I have attractive force dominating, but when they are very close by, repulsive forces are dominating. Okay, so somewhere in between these 2 points where the attractive force dominates and the repulsive force dominates, there is going to be one particular position in which the atom is going to attain maximum stability. Both the hydrogen atoms are going to have maximum stability in one particular point. Okay, now when I say that they have maximum stability, that is the point where the bond, so-called bond, is formed. Okay, bond, I know bond is nothing but an attractive force. Nothing. That's just an attractive force. Is it not? So when they're coming closer and closer and closer, by there'll be a point where if I come little more close, repulsive force will dominate. If I stay here only, then it is a stable position. Right? If I come little more closer, repulsive force, I don't want that. Right? So there is going to be a point at which they're going to stop. Right? That is the position where they stop. That position, I say that a covalent bond is formed. Okay, makes sense. And that is the point where I'll have minimum energy, because I know energy and stability are inversely related. So the moment they stop, that is the point they have maximum stability, minimum energy, and that is the point where I say a covalent bond is formed. I hope this all makes sense to you. Right now, the same thing, whatever I explained to you now, I will be able to explain them in the form of a graph. Right? The graph looks like this. Right? Say I am going to have.
Sir?
Yeah, tell me.
Sir, how are ionic bonds formed then? For example, in ionic bonds occur usually between metals and non-metals.
Yes.
Metals
yes.
have their own nucleus and electron. Similarly, non-metals have their own nucleus and electron. So when we bring them together, even they will repel, right?
They will repel. It's not like they will be just touching each other like that. They will also be at some position. Some little gap will always be there between the two atoms. Because if they come very close, obviously they'll suffer repulsion. But what you have to understand is, in case of ionic compounds, the first step is losing electron, and that electron is accepted by, it's like this, say sodium. I'm talking about the atom. Sodium atom, chlorine atom comes closer by. Now chlorine is electronegative. So here the electron will go from here to here. That's it. Now once the electron goes from here to here, I form Na plus and Cl minus. Now you have a proper, electrostatic force of attraction because of full cation and full anion. Right? So if you look at the attractive force in this case, and if you look at the attractive force in this case, obviously it is greater. Because here I have fully positive and fully negative ions present. Here it is not like that. Here it is because of the nucleus electron attraction and this nucleus electron attraction. Right? But obviously, if they are going to be very, very close, obviously I understand that there is going to be some repulsion. That is an undeniable factor. Yes, obviously. Okay, but here the attractive force is dominating very much, very, very large.
Yeah, okay,
force.
sir.
Yeah, that's
so even if they are close to each other, the attractive force will be more dominant than the repulsive.
Correct.
Okay.
Correct. Right? Yeah. Okay. So whatever I explained to you now in the terms of attraction, repulsion, stability, minimum energy, bond formation, all these things can again be explained in the form of a graph. Okay. So the graph goes like this. Okay. Now, this is my potential energy of the system. Two hydrogen atoms together, their energy. And this in the y-axis, I am going to take the internuclear distance. Basically, the distance between these two nuclei. This nucleus and this nucleus, the distance is what I'm taking here. Okay, right, fine. So let us start at a point where the distance is very large. Here it is 0, right? Here it is increasing. So let me start at a point where the distance between the two nuclei is very high in the sense that they're isolated. Is it not? Now, when they're isolated, their energy is pretty high, right? The energy is pretty high, right? Now, what is going to happen? I am going to make them little come closer so that the attractive force kicks in. Now, I don't have to do anything. They will come closer and closer and closer. Is it not? They will come closer and closer and closer, and they're going to become more and more and more stabilized. Now, if I'm going to have more and more stabilization, now see, this is a negative value. This is negative potential energy. Right? So when I say the internuclear distance becomes little closer and closer and closer, and what I'm seeing is that the negative value of energy is increasing. That means what? More and more energy will be released. Right? More and more energy will be released. Right? More and more energy will be released means obviously what is happening? That it is becoming more and more stable. Okay. So as they come closer, they are going to become more and more stable. And there will be a point, right? There will be a point where that is the maximum distance they can come closer. If they're going to come little more closer, as I told you, the repulsive force will dominate. Okay. Again, the repulsive force will dominate. That will increase. That will decrease the stability, and obviously it will go on keeping like this. keeping on going like this. Okay, now the point which we are interested in is this point. This is the point where I have minimum energy, or say the maximum amount of energy is lost. Okay, this is the point where I have minimum energy. This is the point where the bond is formed. Okay, and this is the point where I have maximum stability for both the hydrogen atoms. Okay, now at this point you will have some internuclear distance, correct? At this particular minima, right? At this particular minima where I have maximum stability, where the bond is formed, I will have some d value, right? Now that d value is what is called as my bond length. Very, very simple, right? The internuclear distance at this minima where I have maximum stability, that particular distance between the two nuclei where the bond is formed is what is called as bond length. Okay, right? So this is how we explain in form of a graph. Logically explaining in the form of a graph explaining, both the things will give you the same thing. Okay, now we understood how is it that a covalent bond can be formed. We understood that. Okay, right. Moving on. Any questions anybody has in this regard?
Can you explain bond length?
Yeah, sure. So the hydrogen atoms will be here, right? One hydrogen atom, second hydrogen atom. There will be some distance between them. They cannot come any more closer. Correct. So this is the point there where they have maximum stability, right? So there will be some distance between them. Correct. That distance is only given here in the y-axis, in the x-axis, right? Now that distance between the two nuclei when I have maximum stability is what is called as the bond.
Okay, sir.
Okay, right, fine.
Sir?
Yeah.
So the maximum stability will be attained at the point when the attractive force is about to end.
Correct. And the repulsive force is
Repulsive
going
force
to
about to
start.
start. Yes.
Exactly. Exactly. Okay, right. So that's about how a covalent bond is formed. Okay, right, fine. Now we understood how a covalent bond is formed and all, but we have to look at different theories which tells us about different aspects of a covalent bond. Okay, so starting with this, right? Like say now we understood that the nucleus is attracting the electron. How many electrons should be there? Say what are the other rules which you have to follow for forming a covalent bond? That insights we'll try to understand. Okay, right. So now the first scientist who spoke about your covalent bonds is this guy Lewis. Okay, so basically we are going to study about Lewis theory. That is what we are going to study. Okay, right. Now what does Lewis theory says is that now before any theory for that matter, first thing what you have to understand is for one covalent bond, 2 electrons should be there, right? Obviously 2 electrons means 1 from each atom. That obviously should be there. Is it not? Like you can understand here, hydrogen 1 electron, this hydrogen 1 electron. Now those two will be shared mutually and you have a bond between this hydrogen and hydrogen. That's how it is. Okay. So for each covalent bond, I require 2 electrons, and in 99.999% of cases, 1 electron will come from 1 atom. Okay, but there are cases where there is a bond, there are 2 electrons, but both the electrons will come from 1 atom, not like 1-1. We'll see that. That is what is called as a coordinate bond. We'll see that later. Okay, so generally speaking, 2 electrons should be there for 1 covalent bond, and 1 electron should come from each of the 1 atom. Okay, right. So now, what does Lewis says? Okay, this is a common point for all the covalent bonds. This is not Lewis theory. So what Lewis theory says is that the sharing of electron, right? The mutual sharing of electron should be done or is done in such a way that octet or duplet rule is satisfied. Right? The mutual sharing of electron, how many number of electrons are shared, or how many amount of electrons you have to give for forming a bond depends on octet or duplet. Very, very simple. Actually, he was the one who talked about octet and duplet. He was the one who introduced octet or duplet. We already know what is octet or duplet. Is it not? The valence shell should contain 8 electrons, or in case of duplet, the valence shell should contain 2 electrons for it to become stable. Is it not? Now you must have already studied these Lewis dot structures in your lower classes. We'll again see it now. We'll spend some 5-10 minutes on this. Okay. Say, let me start with some simple molecules. Say I start with H2. Okay. Now there are 2 hydrogen atoms, right? Each of the hydrogen atom has one electron. Now see, when I put this cross or dots or circle, you can use anything. Okay. This, when I put this cross or this thing, these are what are called as the dots. Right. Okay, fine. So now you understand that this hydrogen atom requires one more electron to satisfy its duplet. Is it not? This hydrogen atom requires one more electron to satisfy its duplet. Same goes with this hydrogen. Is it not? It requires one more electron to satisfy its duplet. So what is going to happen? This hydrogen atom is going to take up this electron, and this hydrogen atom is going to take up this electron. Now you see in the common area, there are 2 electrons. These 2 electrons are mutually shared between both these hydrogen atoms. Okay, now you see there is one pair of electrons shared. There is always one bond. I write like this, H bond H. Like this, whatever you wrote here is what is called as your Lewis dot structure. Okay, right. Let me take another example. Say for example, I take O2 molecule. Okay, now please understand, O2 has so many electrons. We have to take the electrons which are there only in the valence shell. Remember this. Okay, we have to take the electrons which are there only and only in the valence shell. Right. So now you have 2 oxygen atoms. Right. Now I know the configuration is 2,6. Right. The configuration is 2,6. Right. So it has 6 valence electrons. Each of these oxygen atoms has 6 valence electrons. Let me draw the 6 electrons. 1, 2, 3, 4, 5, 6. Okay. And this also has 6. 1, 2, 3, 4, 5, 6. Right. Now what I understand is this oxygen atom and this oxygen atom, both of them requires 2 more electrons to satisfy its octet. Is it not? Both the oxygen atoms require 2 more electrons to satisfy its octet. So what will happen? This oxygen atom already has 6. It will take up these 2 electrons, and this oxygen atom already has 6, requires 2 more. It is going to take up these 2 electrons. Okay, right? So now you see there is one pair, second pair. So how do I write the structure? This is how I write the structure. O double bond O. Right. Now, what you understand here is that there are valence electrons. There are 6 valence electrons in each of the oxygen atom, but out of them, only 2 are getting shared from each of them. What happened to the other 4? The other 4 are there in the valence shell, but not involved in bonding. Okay. So please remember, electrons which are there in the valence shell but not involved in bonding. Right? Now those electrons are what are called as lone pairs of electrons. You have this very, very important term. Okay, there are valence electrons, but only some of them will involve in bonding. Some of them will not involve in bonding. Right? The electrons that are involving in bonding are called bonding electrons. Okay, you can take this down also. Electrons in bond are called as bonding electrons. Right? And the electrons that are there in valence shell but not involved in bonding are what are called as lone pairs of electrons. Okay, so now how do we write the proper structure? Obviously, you have mentioned the bonding pair of electrons. A bond, 1 electron. Here. 4 electrons are gone. Right? Now each of the oxygen atom has 4 more electrons left out. Okay, I represent it like this. Okay, this is how the proper Lewis dot structure you write. Okay, you put the bonds and you check for any lone pair is present. Now, if I ask you, how many lone pairs are there in each oxygen atom? Right? The question is, how many lone pairs are there in each oxygen atom? What will be your answer?
2.
2. Right? There are 4 electrons. right? There are 4 electrons are not 1, 2, 3, 4. 4 electrons are not there which are not involved in bonding, but I'm talking about a pair. One pair is 2 electrons, is it not? So each oxygen atom in this case has 2 lone pairs. LP represents lone pair. Okay,
Sir?
so you, yeah, tell me.
Sir, is the lone pair outside of the bond or like inside of the bond?
What do you mean by outside of the bond? Like whichever is not involved in the bond is a lone pair. That's it. The
Oh, okay,
valence electrons which are not involved in a bond are what are called as lones.
Okay, sir.
Okay, good, good. Okay, so now that we understood, I mean, we understood now what do you mean by a lone pair? What do you mean by a bond pair? Bond pair are valence electrons that are involving in bonding. Lone pairs are valence electrons which are not involved in bonding. As simple as that. Okay, right. Now, can you try the structure, Lewis dot structure for N2? First, you make this, whatever the circles, and then you draw this kind of structure also. Go for it. I'll give you 2 minutes time. Go for it.
Done, sir.
Okay, good. Let me give some time
Done,
for
sir.
everybody. Good, 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 good. If you're done with it, then go for H2O molecule. Draw the structure.
Done, sir.
Good. Let's wait for 30 more seconds. N2, then we'll go for H2O. People who have completed N2, go for H2O. People who have completed H2O, go for ammonia. If you complete this also, then you go for CH4. Then that's it. Actually, instead of CH4, you go for C2H4. It's a little complicated structure. We'll do that. Right? Okay, let me do it for N2. Right? So N, another N. Now I know nitrogen has a configuration of 2, 5. So it has 5 valence electrons. 1, 2, that only, right? Okay, 1, 2, 3, 4, 5. Same way, 1, 2, 3, 4, 5. Okay, now this nitrogen and this nitrogen, both the nitrogens require 3 more electrons to satisfy its octet. So now what will happen? They will take up these 3 electrons and this nitrogen will take up these 3 electrons. Now I understand that there are 3 pairs of electron are there. So this is how we write the structure along with the lone pair. There is 1 lone pair each on nitrogen, on each of the nitrogens, right? Because you see, the 2 electrons are not involved in bonding. 1 lone pair, right? Okay, now I go for H2O molecule, right? Now you understand that the oxygen is going to be in between hydrogen, hydrogen. Hydrogen has 1 electron, 1 electron. Oxygen has 6 electrons. 1, 2, 3, 4, 5, 6. I mean 5, 6. Okay. Now hydrogen requires 1 more electron to satisfy duplet. This hydrogen requires 1 more electron to satisfy duplet, and oxygen requires 2 more electrons to satisfy its octet. So it will take up both the electrons coming from hydrogen. So now you see there is 1 bond here, there is 1 bond here. So how do I write it? OH, 1, 1 bond. Now you have to represent the lone pairs also. There is 1 lone pair here, 1 pair here. 1, 1, 1, 1. That's about, yeah, tell me.
Sir, actually, we are not representing lone pairs here, right? We are only representing the electrons which are not getting bonded. If it was lone pairs, then it should be 2, not 4.
Yeah, correct. The lone pairs, there are 2 lone pairs. That's what I'm telling.
Then why are we drawing 4 dots?
1 pair means 2 electrons, right? 1 pair is 2 electrons. Are you able to get the point? Say, why am I not calling them as 4 lone electrons is because I know in one orbital 2 electrons can be there. That is the reason why we call them as pairs and not individual electrons. Are you able to get the point?
Yes, sir.
Okay, good. Right. So that is the structure, Lewis dot structure for H2O, for ammonia. Right. Nitrogen in here, hydrogen, hydrogen, hydrogen. Each hydrogen has one electron. Nitrogen has 5 valence electrons. See, I am I'm taking only the valence electrons. If you're going to take 7 electrons and put for nitrogen here, you will not get the correct structure. You're going to mess it up. Take only the valence electrons. Okay, say 1, 2, 1, 2, 3, totally 5. Now hydrogen requires 2 electrons. This hydrogen requires 2 electrons. This hydrogen requires 2 electrons. And nitrogen, I know, requires 3 electrons to satisfy its octet. So done. So one bond here, another bond here, another bond here. So we write like this, along with the lone pair, one lone pair on nitrogen, because that is not involved in bonding. Right. Now the last structure, that is C2H4. Right. Now you have to understand that carbon will be together. Hydrogen, 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 hydrogen. Okay. So now carbon has 4 valence electrons. Remember, carbon atomic number 6. The configuration is 2,4. So 1, 2, 3, 4. 1, 2, 3, 4. For carbon, it is done. For hydrogen, 1 electron. Okay, now we can just finish for hydrogens first. Now this hydrogen requires 1 more electron. This hydrogen requires 1 more electron. This hydrogen requires 1 more electron. Sorry. This hydrogen requires 1 more electron. All the hydrogens are done. Right now, for each carbon, for this carbon already has 4 electrons, it requires 4 more electrons to satisfy its octet. Okay, now 4 electrons are there, 2 electrons are already coming from hydrogen, so 6 electrons are gone. 2 more electrons, these 2 electrons are the one. So I'm going to take, see how am I rounding up very properly? This is how I round it up. Okay, same way for this, I take up all the hydrogen's electron as well as the electron coming from carbon, the next carbon. Okay, so now 1 pair, 1 bond, second pair, second bond, all these are other bonds between CH. Okay,
That's
so if you draw, yeah,
no lone
Sir?
pair in this case.
Sorry, what?
No lone pairs in this case.
Exactly. In this case, there are no lone pairs. Absolutely true. No lone pairs. Because
Sir?
all the electrons involved here are involved in bonding. Yes, what's the question?
Sir, is it important to draw the pattern correctly, like in the hydrogen at a specific place?
No, not required. You can put the hydrogen anywhere, anything
Okay.
which is comfortable for you. Okay, right? I just do it normally. Okay, so now you see carbon is having a double bond. Now there are one CH bond here, another CH bond here. Same way, one CH bond here, another CH bond here. This is the structure for C2H4. Okay, right? So this is how you draw the Lewis dot structures. This should have been taught in your 8th or 9th class. If you didn't know now, if you didn't know then, now you can know how to draw this. Very, very important. Okay, right? Now this is not going to be like say as important. Like it's in the sense that it is very important to understand the basic things. That's what is the point. Okay, right. So done. That's about the Lewis dot structures. Now, why are we not following this? This does not give so much information. What are the demerits? Right? What are the demerits of Lewis theory? Right? Lewis theory is that it does not talk about the shape of the molecules. Right? Does not talk about the shape of the molecule. Or the first and foremost drawback is that you will see that there are molecules which doesn't obey octet or duplet. Okay, there are molecules, right? There are compounds in which the octet or duplet is not satisfied. It is actually can have more than 8 electrons, less than 8 electrons. All these things are possible. Okay, now I'll give you some examples. Say, for example, take the case of PCl5. phosphorus pentachloride. Okay, PCl5 is a compound. Okay, now you look at this. PCl5, phosphorus belongs to the hydrogen family. So again, it will have 5 valence electrons in it, right? So now you look at this. 1, 2, 3, 4, 5 electrons. Now chlorine has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Same way, another chlorine. 1, 2, 3, 4, 5, 6, 7. Another chlorine. I'll make some space. Another chlorine. 1, 2, 3, 4, 5, 6, 7. Another chlorine. 1, 2, 3, 4, 5, 6, 7. Another chlorine. 1, 2, 3, 4, 5, 6, 7. Okay, chlorine, no problem. Chlorine will take up this electron. Each and every electron which is there nearby, chlorine will take. Not a big deal. Chlorine octet is satisfied.
Phosphorus will have 10 atoms.
Exactly. Now see, phosphorus already has 5 electrons. Now if it is giving 1 electron to chlorine, obviously it will take up 1 electron, right? So you will see that all the 1, 1, 1 electrons are taken by phosphorus, right? You will see that there are 5 bonds. Okay. Now you see that phosphorus has 10 electrons in its valence. Okay, I can draw the Lewis-Dot structure. Lewis-Dot structure can be drawn, not a big deal. That's very simple. But if you the very core reason, like or say the core point of Lewis is the octet or duplet rule. That itself is getting violated here. Okay, in this case, you see phosphorus is having 10 valence electrons. Right now, I can give you one more example. Yes, any questions?
Yes, sir. Sir, is there a molecule like PCl3?
PCl3 is properly octet, right? Because you see 5 valence electrons for this thing, 3 more electrons will come from chlorine. This will be 8. No problem. PCl3 is okay, but PCl5 is a problem. It's not octet satisfied. It is more than that. Like these kind of compounds, I will call them as expanded octet. Okay, this is what is called as expanded octet. Okay, there are reasons for this. Okay, why? Say for example, NCl3 exists, but NCl5 doesn't exist. But see, for PCl3 exists, PCl5 also exists. Okay, you can do it as a homework. Why is it like this? Take it as a homework and tell me next class why is it like this. Both phosphorus and nitrogen belong to the same group, right? Same family, right? But NCl3 exists, but NCl5 doesn't exist. But here, PCl3 and PCl5 both are existing. Why is it like this? Okay, check it out and tell me the answer next class. It's a homework to you. Right, check it out. Okay, so now these are what are called as expanded octet. Now in this case, I have 10 electrons. Now I can even show you a case where I can have 12 electrons possible in the valence shell. The example is SF6. Right, now you see sulfur belongs to oxygen family. It will have 6 electrons in the valence shell. Now there are 6 chlorine atoms. Each 1 electron it will give. Totally how many electrons then? 6 electrons. So 6 plus 6 will become 12 electrons. Again, you can draw the Lewis-Dot structure and check. You will find that sulfur, for fluorine it's okay, no problem. But for sulfur, you will find that sulfur is having 12 electrons in the valence shell. Okay, again, it's an expanded octet case. Right. Now, let us take a case where I have less than 8 electrons in the valence shell. Right. So the best example I can give you, there are 2 examples I can give you. One is beryllium chloride. The other one is BF3. Okay. Now beryllium, you check. Beryllium is having a configuration of 2, 2, right? 2 valence electrons. 1, 2. Same way. Chlorine is having 7. Okay. Now chlorine requires 1 electron to satisfy its octet, so it will take up this electron. This chlorine will take up this electron. Now only 1 electron is given, so only 1 electron can be taken. So what will happen now? Beryllium will take this one, already existing electron, and this one. You will see there's a bond here, there's a bond here. So BeCl, Cl. Now you can even represent the lone pair. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. I mean 3 lone pairs, 6 electrons. Okay. Now what you understand is beryllium has 2 valence electrons, and 2 more electrons are coming from chlorine. So how many electrons totally? Only 4 electrons are there in the valence shell of beryllium, right? But what I need to have is 8, right? But this is less than 8 electrons. Same goes with BF3. BF3 you check. Boron has a configuration of 2, 3, 3 valence electrons. 1, 2, 3. Fluorine is having again 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. Now fluorine requires one electron. This fluorine requires 1 electron. This fluorine requires 1 electron. Octet, okay, right? But again, 1 electron gives only 1 electron it can take. So it will take 3 more electrons, each from 1 from fluorine. So 3 plus 3 will become only 6 electrons in the valence shell. Last time I had only 4 electrons in the valence shell. This time I'm having 6 electrons in the valence shell. So now there are more. What you have to understand is there are molecules which are having less than 8 electrons in their valence shell. There are molecules where the atom is having more than 8 electrons in the valence shell. Okay, so the very core point of octet, the very core reason of Lewis, that is octet or duplet, that itself is violated, right? And Lewis was not able to explain the bonding in the case of these kind of molecules. He was not able to give a proper reason why this is happening. Okay, but other theories which you're going to see in today's class or the next class, they were able to explain why are these things okay. Even though octet is not satisfied, how is it that these molecules are getting stabilized, right? Because till now, the only criteria for stability is octet. That's what till now, that's what you have been studying. But you will know that you will study that octet or duplet is not the only criteria. There are so many other criteria for me to understand, for me to get stability, for the atoms to get stabilized. Okay, so these are all the problems. So the first problem I said, the main problem is there are species which does not follow octet or duplet rule. Second thing is that the shape of the molecules, like say, if I have only 2 diatomic molecules have no shape, right? But if it is a polyatomic molecules, obviously there can be some shapes and all coming, right? I'll tell you what are the shapes when you go for the next theories. Those shapes were not explained. The other thing which is not explained is the strength of the bonds. Right, strength of the bonds in the sense, say one bond is stronger, another bond is weaker. Why? All the covalent bond, how is it formed? All these things he told. But why is it that certain bonds are stronger, certain bonds are weaker? Again, he was not able to explain. Right. And the other thing he didn't explain is about why certain compounds are colored. Right? Why certain compounds are colored, whereas certain compounds are not. Right. Say another thing is the magnetic properties. Right, certain compounds will get attracted towards the magnet. Certain compounds will not get attracted towards the magnet. What is the reason behind all this? Right, nothing was explained. Right, so the main drawback is there are certain compounds that does not explain. That does not obey octet or duplet rule. The other things are shape of molecule is not explained. Certain bonds are stronger, certain bonds are weaker. We don't know why. From Lewis theory, certain compounds are colored. We don't know why. Certain molecules get attracted towards the magnet, certain does not. Why, again, was not explained by your Lewis. Okay?
Sir? Sir, what do you mean by certain compounds are colored?
For example, I know NO2. NO2 is brown in color, whereas NO is colorless. You understand? Both are nitrogen oxygen species only. Right, but one of them is colored, the other one is colorless. Why? Nothing. There was no explanation. This is what I'm trying to say. Yes,
okay,
makes sense. Okay, right. So like this, there were so many problems like this. Okay, so because of this, other scientists came up with the different theories. Right. The next theory which we are going to study is valence bond theory. Okay, now actually I will be combining this with VSEPR. Okay, VSEPR is valence shell electron repulsion theory. Okay, so both of them are different theories, but we'll combine them together and study them together because it will make more sense. Okay, a lot of insights you'll be getting. Right. Okay, fine. So now actually, it is not valence bond theory. Actually, its valence bond theory got updated by someone to something called as theory of hybridization. But again, in your book, in your NCERT textbook, the valence bond theory and theory of hybridization is given to be same, but it is not exactly same, people, right? Valence bond theory was developed by one scientist. I forgot the scientist's name. That had some problem. So little modification were done to this valence bond theory, and then came up your theory of hybridization. Okay, but in 99% of textbooks, you will find that both valence bond theory and theory of hybridization are same. They will not even tell the word theory of hybridization, but these two are different. There were some problems with valence bond, and it got updated to the theory of hybridization. Little modifications were done. Okay, fine. So let us understand the statement of valence bond theory first. Okay, please take down the statement. Right. A covalent bond is formed. A covalent bond is formed between two atoms. A covalent bond is formed between two atoms when the unpaired electrons, in the atoms, when the unpaired electrons in the atoms gets paired. When the unpaired electrons in the atoms gets paired. Okay, that's a statement. The statement goes like this. Covalent bond is formed when the unpaired electrons in the atoms, okay, unpaired electrons, right? Unpaired electrons in the valence shell of an atom. Just include this point, please. Okay, a covalent bond is formed when the unpaired electrons in the valence shell of an atoms gets paired. Okay, right. Now, it's very simple to interpret this, people. Look at this, hydrogen, both of them are having 1s1. Another hydrogen is also having 1s1. So I have one unpaired electron, unpaired. There is no pairing here, right? Now, a covalent bond is formed. They two will come together. They will make another kind of orbital and they will get paired. And this is where I say a covalent bond is formed. Okay, now this will work for all the things. Oxygen, O2 molecules, you check. Oxygen is having 1s2, 2s2, 2p4. Correct, right? Now, obviously, forget about this is paired. In 2s, it is paired, but in 2p, you check. 4 electrons will write like this. Remember Hund's rule of maximum multiplicity. 1, 1, 1, then pairing. Okay, now same way, the another oxygen atom will have the same 2p4. Okay, now you see these two will come together, make 2 electrons, and this will come together to make 2 electrons. So obviously between oxygen, there's a double bond. Okay, as many number of unpaired electrons I have, that many covalent bonds will be formed. Okay, now what they're trying to tell in other words is that the orbitals which are involving the orbitals which has unpaired electrons, okay, the orbitals which has the unpaired electrons will come together, make a new orbital, and they get paired. That's the exact way of putting it. Again, I repeat, the orbitals which are having unpaired electrons will come together, make a new orbital, and that, and in that new orbital, the electrons are getting paired, and that is how a covalent bond is formed. That is what valence bond theory says. Okay, right. But this was able to explain a lot of things, like that isn't based on octet rule. It is not based on anything else. So that problems are taken care of. But if I check any compound in carbon, for example, say I take CH4. Okay, now you look at this. CH4 in carbon, I have 1s2, 2s2, 2p2. Correct, right? So in 2s, the electron is paired, and in 2p, there are 2 electrons. Correct? Now, according to valence bond theory, the number of unpaired electrons, how many ever unpaired electrons I have, that many bonds only the molecule can form. Correct? Right? Now you understand that there are 4 CH bonds here, but according to valence bond theory, only 2 bonds can be formed because only 2 unpaired electrons are there. Is it not? Now that is where the problem lies. That is where it got updated to this theory of hybridization. Okay, that is where it got updated to theory of hybridization. Now, what is the time? Can I start? No, actually, guys, we'll stop with this for today. Okay, so
Sir,
yeah, tell me.
could you repeat the last thing which you said?
Yeah, sure. What I'm trying to tell, I know the formula of methane is CH4. That means in this case, I have 4 CH bonds. Correct? Right. Now, what valence bond theory says, there should be unpaired electrons in the valence shell. Right? Now, those unpaired electrons will get paired with the unpaired electrons of the other atom so that a covalent bond is formed. Yes? Right? Now, look at this. I have a configuration of carbon to be 1s2, 2s2, 2p2. Right? 2s electrons are completely paired. In 2p, I have 2 unpaired electrons. Okay. Now, as many as the number of unpaired electrons I have, that many bonds will be formed. So, according to valence bond theory, carbon can have only 2 bonds. But what is in reality happening? Carbon will generally form 4 bonds. Is it not? That is the problem with valence bond theory. That's what I'm trying to say. Yes, understood?
Yes, sir.
Okay.
Sir?
So, yeah, tell me.
Sir, then in case of PCl5, phosphorus should form only 3 bonds, right?
Exactly. Correct. So all these things are not explained. That is why the theory got little modified to theory of hybridization. So we'll see how, like these notes are almost the same only, but this particular problem which I'm telling, right, the number of unpaired electrons, that little got modified in theory of hybridization. We'll see how is it modified, how is it able to explain all the things which were not explained in the case of Lewis theory, but still like valence bond theory or the theory of hybridization still doesn't explain so many things. That we'll see at the last. What it explains, we'll see thoroughly, and what it doesn't explain, we'll see at the last when we complete valence bond theory. Okay, fine. I think we'll stop with this for today, people, because I don't want to start theory of hybridization and leave it in between. I want some continuity. That's why I'm finishing 10 minutes or so late. I mean, 10 minutes or so early. You can go enjoy the time. Okay. Is there any questions anybody want to ask me? Okay, fine then. I'll stop right here. Thank you so much, people. We'll meet again on next class, whenever the next class is. Thank you so much. I'm ending the class.
Thank you, sir.
Thank you, sir.
Thank you, everybody.